Welcome to Physics 30 Prep Fast Track, lesson number 5, Kinematic Formulas, A. And we're going to look at a number of different kinematic formulas. Now that we've discussed what velocity is, what speed is, what acceleration is on a basic level, and looked at some of the ideas involved with the graphing and so on, we want to derive the formulas for you. And so what we'll do is we'll take a look at velocity time graph. All right, this particular one is one that we're familiar with from previous examples. When you take the slope of a velocity time graph, what do you get? Well, you should know that you get acceleration. The slope formula is rise over run, or in other words, slope is equal to the acceleration. Acceleration is equal to the rise over the run. And the rise of the run, of course, can be shown in a number of different ways, but basically you use your ordered pairs and so on. The rise over the run is equal to the change in velocity, which is the rise, over the change in time, which is the run. And when we put this by definition, change is final minus initial. All right, anything that changes can be determined by taking the final state and comparing it to the initial state. For example, if you get a raise at work from, let's say, $12 an hour up to $15 an hour, then of course your change in pay is your final, which is now 15, minus your initial, which was 12, and of course 15 minus 12 is a change of 3. So we can use that definition of change to come up with this formula, that acceleration is equal to the final velocity minus the initial velocity over time. Or in other words, the change in velocity over the change in time. Quite often, not always, but quite often with time, we don't know, there's not an initial time and a final time, but just the time that's elapsed, like using a stopwatch. Since the initial time is 0, then whatever t is afterwards, that's our change in time. But you have to be careful with that sometimes. So acceleration is defined as the rate of change of velocity. All right, the rate of change of anything is usually something over time. Your rate of pay is how many dollars you get over the time that's elapsed. And of course, this is your first equation. A is equal to VF minus VI over T is the first equation for accelerated motion. You will be getting a number of different equations that you will use in problem-solving situations in Physics 20, 30 Prep here, and going on to Physics 30, and even in your post-secondary courses. You'll always be given a number of formulas on a sheet or a data booklet. You don't have to memorize these, but you should become very familiar with them. So with that first equation, this is the first of 4 expressions or formulas you'll use in kinematics, the study of motion. And the best way to learn how to use these is to apply them in a problem-solving situation. And you'll be given an extensive practice assignment after the 8th lesson, all right? So we're going to introduce a number of formulas, and then you'll be given lots of practice to work on. And there are some quizzes and so on that you can use to assess yourself before you write any exams or quizzes. This first example is quite an easy one. All right, it doesn't involve any formula manipulation. It doesn't involve anything really that difficult other than substitution and understanding what it is that you're reading. So here's a cyclist. A cyclist accelerated uniformly from rest. Now, what does that mean, rest? Well, rest means you're not moving. And that means that the cyclist's initial velocity must have been 0. And so already you know that VI is equal to 0. So that you would substitute into that top formula. The next one, 6.8 meters per second, well, that is your final velocity. So you know your initial is 0, you know your final is 6.8. And of course it took how long? It took 4 seconds. So what you need to do is take this formula and use the information that's been given. And I'll give you a quick example of that. So knowing that the initial velocity is 0, you would substitute 0 right here. And knowing that the final velocity is 6.8, you would put 6.8 here. And of course, knowing that time was 4 seconds, you would put 4 seconds here. And then, of course, you would take those values and substitute them, and you should get something close to 1.7 meters per second squared as your answer. So that's a fairly straightforward little problem. All right, the next one is a little more of a challenge. In this problem, what you'll have to do is you'll have to solve or manipulate the formula for the unknown. And in this case, the formula or the problem is that a car was accelerated uniformly from rest at a particular rate of acceleration. The final speed was 30 meters per second. What was the acceleration time? Now, in order to do this problem, because you are not given VF and VI and T and just substitute that in to get A like you did on the first equation, you need to manipulate this formula and solve for T. And I've shown you the manipulation, the standard formula on the left, and then the manipulated version on the right. What I did was I multiplied both sides by T and divided both sides by A. And in this case then, once you know that the initial speed was 0, the final speed was 30 meters per second, the acceleration was 3.75, when you substitute those into this equation again, you get an answer that is very close to 8.00 seconds. So that was the acceleration time. All right, so you'll get lots of practice on these, but there's a simple example. Formula manipulation is a useful tool in doing these. In this final example, using this formula, we'll again have to manipulate the formula for the unknown. In this case, the unknown is going to be VF. And of course, what I'll do is I'll give you the initial velocity, I'll give you the acceleration and the time, and I'll say, all right, you're going at a certain speed, you accelerate at a certain rate for a certain period of time, and what is your final velocity? So example number 3, a train was accelerated uniformly from rest. Of course, that means that the initial velocity was 0 at a rate of 1.25 meters per second squared for a period of 18 seconds. So here's a train starting from rest, pulling away from the station at a fairly slow rate of 1.25 for 18 seconds. What's the final speed of the train? So 0 plus 1.25 times 18 will give you an answer of very close to 22.5 meters per second. So that should work. This example, you should take a look at it, try it on your own, and also see if you can work out this substitution. Start with this formula and see if you can manipulate that in order to get solve for VF. It involves a number of steps. The first step would be multiply both sides by T. That removes the T from the bottom of the right-hand side and moves it to the top of the left. Then, in order to solve for VF, you'd need to move that negative VI from the right-hand side to the left-hand side. It would become a positive VI. And so you end up with AT plus VI equals VF, or that's exactly what this says in a slightly different way, but basically the same thing. So there's a few examples that you need to work on. You'll have lots like this in the problem set that's assigned shortly. All right, once you've gone through a number of these equations, then we'll assign practice on all of them.